Hi there. Very often in stoichiometry, you will be asked to find the limiting reagent, percentage yield, or maybe even the percentage purity. What are these three things? The limiting reagent, which is sometimes just referred to as the limiting reactant, is simply a reactant in a chemical reaction that when get used up, the reaction will stop happening because there will be lack of one of the reactants. Percentage yield is simply rating the amount of substance that is produced in a chemical reaction using a scale of 1 to 100. On the other hand, percentage purity is simply rating how pure a certain chemical substance in the chemical reaction is. Again, we're using a scale of 1 to 100. This scale of 1 to 100 is just known as percentage. As you can see, percentage yield, percentage purity. This is Z Online School. In this video, you and I are going to be looking at more concepts involving stoichiometric analysis. We are going to do this in a systematic way, and by the end of this video, you will be comfortable with determining the limiting reagents, which are also known as limiting reactants, calculating the percentage yield, and the percentage purity. At the end of this video, we've got bonus tips for you. Make sure you watch this video till the end to get the maximum value out of it. Let's start with looking at the limiting reagents, which are also known as limiting reactants. We're going to get the definition of a limiting reactant with us first looking at the definition of limit. Limit simply means to stop something from increasing beyond a particular amount or level. Now, what's the relation between limit and limiting reactants? As you can see, the word limiting has the word limit in it. Therefore, a limiting reactant is a certain reactant that does what we're talking about here, limiting the reaction to take place. In this video, I would like you to get going with the definition: a reactant that, when used up, causes a chemical reaction to stop occurring. Right here, it's very important to get the difference between a limiting reactant and an inhibitor. These two things might be confused if you don't really understand what a limiting reactant is. A limiting reactant will cause the reaction to stop because it's not part of the reaction. But an inhibitor will stop the reaction because it's present as the reaction is happening. It's very important to know this key difference between limiting reactants and inhibitors. And don't forget our definition of a limiting reactant. It's very important, especially this part which says when used up. Let's look at some questions on how to find this limiting reactant or how to determine the limiting reagent. It's not a very difficult process. We'll be just using the more concepts to help us see which of the substances, which is the reactants, is getting used up first. Here we've got a chemical reaction of lead 2 nitrate and sodium chloride as shown below here. You shouldn't have a problem interpreting anything here. We've covered a lot about the more concept and stoichiometry, so you should be comfortable. We've got 15 grams of sodium chloride that are being used here and 16.8 grams of lead 2 nitrate that are also used in this chemical reaction. Now, which of these two, sodium chloride or lead 2 nitrate, is limiting the reaction from continuing when it gets used up? It's very easy to find this when we have the number of moles. Note that we've got the standard mole ratios here. 2 moles of sodium chloride should react with exactly 1 mole of lead 2 nitrate and produce the respective substances. So let's try to find the number of moles and see if actually we had 2 moles of sodium chloride reacting with 1 mole of lead 2 nitrate. Let's start with finding the number of moles of sodium chloride. The procedure isn't so difficult. As you can see, we're going to get the mass there, 15.3 grams of sodium chloride, we've been told that, and we're also going to get the molar mass of sodium chloride. Molar mass just simply meaning the mass of sodium chloride that is equal to 1 mole. As you can see on screen, we've got the elements sodium and chlorine. We're going to get their relative atomic masses and add them. Hence, as you can see, our molar mass, or the mass of 1 mole of sodium chloride, should be 58.5 grams. Now we're going to use that 58.5 and use it in the calculation. As you can see, it gives us this answer. It would be helpful for yourself if you did this calculation also on a calculator, so that you can get used to this process also. I'm just going to get 4 digits, 2, 6, 1 and 5. As you can see, we can't round off and get a different number here for the 5. Therefore, N will be equal to 0.2615 moles. These are the number of moles of sodium chloride that we have if we used 15.3 grams. Now let's do the same for lead 2 nitrate. 60.8 is the mass, and now our job is finding the molar mass. The molar mass for lead is 207 or 207, so we're going to add it to the mass of nitrogen in this compound. As you can see, we've got 2 molecules of nitrate, therefore we've got 2 nitrogen atoms. Hence 14 times 2 gives us that 28. We do the same for oxygen. If you want, you can do 16 multiplied by 6 somewhere else, but you can do that on a calculator by just bringing some brackets, so that this is a separate calculation. As you can see, the relative atomic mass of oxygen is 16, so it's there. The number of atoms of oxygen here are 6, and that's how we get this. We hit equals and get the molar mass for lead 2 nitrate. Now our job is calculating this and simplifying it using a calculator. As you can see, we've got 0.18368. I'm using 4 decimal places still. As you can see, we've got an 8, which is bigger than 5. Therefore, when we round off to 4 decimal places, it's going to give us 0.1837. N is equal to 0.1837 moles. Now, what we're going to do here is just find a way of proving which of these two is more than the other or less than the other. Remember that I said we need 2 moles of sodium chloride to react with 1 mole of lead 2 nitrate. Now, are these number of moles in that ratio, or we have one of them that is more or one of them that is less? We're going to do that just like we want to use more ratios to find an unknown amount of moles. You can see this is the standard mole ratio, 2 to 1, the sodium chloride to the lead 2 nitrate. Now, I'm going to use the sodium chloride, but you can also use the lead 2 nitrate. It's one and the same thing. I got the moles of sodium chloride here, which is 0.2615, and then I make a ratio with an unknown amount of moles or number of moles for lead 2 nitrate. What I'm trying to do here is just finding the number of moles of lead 2 nitrate that are required to react with exactly this number of moles of sodium chloride. If you use lead 2 nitrate, you'll be finding the number of moles of sodium chloride that are required to react with exactly 0.1837 moles. Here I'm using proportion, therefore I'm going to cross multiply and get an equation. 2x is equal to 0.2615. Now I find the value of x by simply dividing both sides by 2, because that x is multiplied by 2, and getting rid of that multiplied quantity, I just divide by that same quantity I don't want. The 2 and the 2 here are going to cancel out, so I'm going to have x is equal to this simple expression. I can simplify this using a calculator, but instead of using this value, I'm going to use the 15.3 divided by the 58.5. I guess you can see I want the accurate answer. This one was rounded off. I want to use the one that wasn't rounded off, then divided by 2. My answer, as you can see, is 0.13076. When I round off to 4 decimal places, I have an 8 instead of a 7. Therefore, x is equal to 0.1308. Now, the question here is using this number of moles we found, can we determine which one is the limiting reactant? Yes. What we're going to just do is now start some comparisons. If I used 0.2615 moles of sodium chloride, I need only 0.1308 moles of lead 2 nitrate. However, as you can see, in the 60.8 grams of lead 2 nitrate, I have 0.1837 moles. Therefore, it's very easy to see that the number of moles for lead 2 nitrate are more than required. Hence, if this lead 2 nitrate is more than required, it means it's the one in excess. Therefore, the one that is the limiting reactant, or the one that is in small amount, is the sodium chloride. Therefore, when this 15.3 grams of sodium chloride depletes, the reaction stops because there's nothing to react with this remaining lead 2 nitrate. Hence, we found the limiting reactant. Now, let's do a quick workout here of the excess reactant. The excess reactant is just the other reactant that is not limited in amount. They are kind of opposites. As you saw, we found the excess reactant, then we made the simple intuitive guess that the sodium chloride was the limiting reactant because the lead 2 nitrate was the one that was in excess. Now, sometimes in a part B question, you might be asked to find which reactant is in excess. Hence, you will have to do the same calculation, but since we've done it already, we know that the one in excess is the lead 2 nitrate, and the only thing we're going to worry about is how to find by how much that lead 2 nitrate is in excess. We're going to do something very simple. We're going to use the number of moles still. Remember, this is the mole concept, and we'll be using a lot of the mole. We can find the excess amount of lead 2 nitrate by simply getting the actual moles and subtracting them with the theoretical moles. The actual moles of lead 2 nitrate are those number of moles that are in this 60.8 grams of lead 2 nitrate. The actual number of moles that are used in the chemical reaction. The theoretical number of moles are those number of moles that are used by means of calculations. It's like that amount we found. The theoretical moles are simply the amount of moles that were used to deplete this sodium chloride that is found in the 15.3 grams. As you can see, it's not a difficult calculation. Our number of moles that are in excess are 0.0529. That's the number we're going to use to find the amount of lead 2 nitrate that is in excess. Now, we're going in the right direction. What we need to do is convert this number of moles of lead 2 nitrate into mass. As you can see, all of our information here was given in mass. So when they ask us to find by how much, they're obviously talking about the amount of mass by which this lead 2 nitrate is in excess. This is not difficult because we know that we've got a mass formula, and if we just make m the subject of the formula, we can find the mass. We're going to do this using this simple triangle. Our m and our mr are divided there, so our m will be on top and our mr there will be here below. Our n is what we were finding, and now we're just going to cover m and see what remains. When we cover m, you see that we're left with n and mr. And if you can remember, I said that this here simply means multiplication. So mass can be gotten by multiplying the number of moles by the molar mass. I can remember we calculated the molar mass for lead 2 nitrate. Therefore, I'm not going to do it again, hoping you got it the first time. Mass will be equal to this number of moles, the 0.0529 multiplied by the 331. Luckily, we have our answer there. I'm not going to start doing more work. My calculator can save my answer. I was just from finding, and yeah, I hit equals, and you can see 17.509. The mass of this lead 2 nitrate that was in excess was 17.5099, as you saw. Therefore, we can say this excess rounded off to 3 significant figures is 17.5 grams. Even though the difference in moles is very small, as you can see, the difference in mass will be a very huge number. So make sure you do your calculations accurately so that your answers are as accurate as possible. Now let's take a look at the percentage yield. What is percentage yield? Or let's say, what is yield to start with? Yield is simply the total amount of crops, profits, etc. that are produced. This is chemistry, so we're talking about substances, elements, and all these chemical compounds. So when we say yield, we're referring to the total amount of substance that is produced. Now, when we talk about percentage yield, we are finding a way of expressing this total amount of substance that is produced using a scale of 1 to 100, or just simply converting that amount of substance produced into a percentage. Let's see how we do that. To do this, we need a formula, and this is the formula. Percentage yield is equal to the actual yield divided by the theoretical yield multiplied by 100%. Now, it's very important to note what these two things are and how you'll be able to know which is which in a chemical reaction. In a chemical reaction, the actual yield is the amount of substance produced after an experiment has been carried out. So it's the yield physically. What you yield as you are seeing and performing the chemical experiment is the actual yield. Just like we had the actual moles, which are the actual moles or the exact moles that were provided in the experiment. Even here, the actual yield is the yield you get from the experiment. Theoretical is now calculated yield, or simply the amount of substance that is supposed to be produced if the experiment is ideal. When we say ideal, we just mean 100% efficient, meaning there are no errors, there's nothing disturbing the chemical reaction. Unfortunately, this is rarely the case. Hence, your yields or percentage yields will be less than 100%. They might be close, but they'll be usually less than 100%. Let's get to a question and understand how we can find the percentage yield. It's very simple. Here we've got a nice question that I found. We're going to learn a lot from it. We've got ammonia that can be produced by the reaction of hydrogen and nitrogen, which is the Haber process, obviously. Now we're being told 90 grams of nitrogen was reacted with 19 grams of hydrogen, producing 92 grams of ammonia. We're asked to calculate the percentage yield. As you can see, we've been given two reactants, and fortunately enough, we've been given information about both of them, 90 grams of nitrogen and 19 grams of hydrogen. Which one are we going to use? Well, what we're supposed to do is find which of these two is the limiting reactant, just like we did earlier. So we'll just do that. (90) divided by the 28 is the calculation we want to find the number of moles of what? Nitrogen that are used in this chemical reaction. You can see it's 3.21428. Again, I'm getting 4 decimal places to be accurate. So we're going to have 3.2143. N is equal to 3.2143 moles. This is the number of moles of nitrogen in that 90 grams. The molar mass of nitrogen is 28. So if you have 28 grams, you have 1 mole. Luckily, we had more than enough here. These are gases, so it's very practical that we can have these massive numbers. We do the same for hydrogen. N, the mass of hydrogen is 19. We're going to divide it by 2. Note that hydrogen is a diatomic gas, so for each hydrogen we're having 2. We do that on a calculator, or we can do it mentally. So N is equal to 9.5 moles. What we're going to do is ask ourselves if these two numbers here are exact to this mole ratio, 1 to 3. I'm going to do that on the calculator very quickly. If we have 1 mole of nitrogen, we should have 3 moles of hydrogen. So it must make sense that if I get this number and multiply it by 3, I'm supposed to get the number of moles of hydrogen that were used. As you can see, I've got 9.6428. The difference is small, but like I told you, when we're using moles, this small difference is very big. Hence, we've got more than enough nitrogen, because when I multiply that number of moles for nitrogen by 3, I get an answer that is bigger than the number of moles of hydrogen. Therefore, hydrogen here is the limiting reactant. And because hydrogen is the limiting reactant, it's the one I'm going to use to find the percentage yield. And now when I talk about using hydrogen to find the percentage yield of ammonia, what I just mean is I'm going to use this number of moles to make a mole ratio that will help me find the exact or the theoretical number of moles of ammonia that were formed. You can see the standard mole ratio is 3 to 2. Now our mole ratios here will become 9.5 to x. I do the cross multiplication. Again, I'm using proportion here. If I multiply the 3 and the x, I'm going to have 3x. 9.5 by 2, I just come back to this 19. So 3x is equal to 19. Now I'm supposed to find x. X is combined with 3 by multiplication, so I'm going to divide this x by 3 and the 19 by 3 to get the value of x. Let me do the 19 by 3 in advance. You can see it gives me 6.3. These are recurring digits. So yeah, you can get 4 decimal places and whatever, and use it. Now I'm going to divide by 3. We've already done this process on our calculator, and we have our answer. X is equal to 6.333. The 3's keep on recurring or repeating, and so this is quite a decent answer. These are the number of moles for ammonia that are produced when we have this amount of nitrogen and this amount of hydrogen reacting. Now our job is making this number of moles into mass, and we've done this practically already in this video, so it won't be a big deal. To do that, we're supposed to use this formula. Obviously, mass is equal to number of moles multiplied by the molar mass. Obviously, you know how we got this. We just changed the subject of the formula of N is equal to M divided by MR. And so the 6.333 will be multiplied by the 17. I just hope you're not wondering how we got the 17. Remember, it's the molar mass, therefore we added the 14 for nitrogen and the 3 for hydrogen, and we got the 17. So I get this 6.333, and I'm going to multiply it by the 17. It gives me 107.66. Again, you see some recurring digits. I'm just going to get 4 digits, and therefore it will be 107.666. We round off and we have a 7. Okay, these are the grams of ammonia that are actually produced theoretically, meaning after calculation using the information that we've been given here, we are supposed to produce 107.667 grams of ammonia. If you remember, percentage yield was actual over theoretical multiplied by 100, right? Can you see that our actual number of ammonia is less than this that we found here? We have 92 grams of ammonia being produced, yet actually from what has been provided on the reactant side, we're supposed to provide or produce 107.667 grams. You can see that the theoretical is bigger than the actual. Therefore, we're going to have a number that is less than 100. We simplify this fraction using a calculator. I still have my answer there, so I'm just going to say divided by answer, and I have 0.854489. And as you can see, we'll be multiplying by 100, so this decimal point will just move 2 times towards our right. Let's write what we found so far. Percentage yield is equal to that answer. You can see I still used 4 decimal places, and I multiplied by 100. Like I told you, this decimal point will move 2 places towards our right. You should know that, I'm sure by now. So our percentage yield will be equal to 85.45%. Sometimes you might be required to round off your answer to one decimal place, but this looks pretty good. We're done with how you can calculate the percentage yield. Let's quickly also look at how we can calculate the percentage purity. First, as you know, we're defining these terms and getting to understand where they come from and what they mean. Purity comes from the word pure. Pure, as you can see, means not mixed with anything else or with nothing added. So when we're calculating percentage purity, we're trying to find how pure this thing is. It's not mixed with anything. So when we say something is 90% pure, we're saying 90% of this thing is actually what we need. The 10% is what is added or what is mixed with what we want. So purity can be just simply said the state of being pure or not being mixed with anything. Now, when we're finding percentage purity, we're finding the percentage of the pureness of a particular substance. We'll do that by using this simple formula. Percentage purity being equal to the mass of the pure substance divided by mass of the impure substance multiplied by 100%. Like you can remember, we're using a rate of 1 to 100, which is just simply percentage. It's also very important to note how you will be able to know that this is mass of the pure substance and mass of the impure substance. These two things are key things you should note when you want to differentiate pure substance and impure substance. The pure substance is the actual, we can say the theoretical amount of mass needed for something to happen or for the reaction to get completed. The impure is just the total mass that was used. Let's look at an example for you to get what I mean when calculating percentage purity. In this question, we've been given 15 grams of calcium carbonate, which is reacted with an excess of hydrochloric acid, producing 3,280 cubic centimeters of carbon dioxide gas at room temperature and pressure. We've been asked to find the percentage purity of the calcium carbonate sample. Very simple question, nothing like calculating our limiting reactant here, because we've been told the HCl is in excess, and therefore it makes sense to say that the calcium carbonate is the limiting reactant, and we've been given information about the limiting reactant. Now, what you're going to see here is that this 15 grams of calcium carbonate that we've been given is actually the mass of the impure, because it was what was used totally in the reaction, or it's the total mass of calcium carbonate that was provided for the chemical experiment as was being used. Meaning, we're going to find a certain mass that will be less than this 15 that gave us this yield. And therefore, we're going to use our volume formula. I hope you can remember how to divide those formulas in those three forms: volume, mass, and concentration. You can remember N is equal to V over mV. If you've watched the video about application of the mole concept, obviously that's our volume formula. Now, very simple, we're going to get our V, convert it into cubic decimeters, and that is simple also. We've done those conversions in our previous video, so we get that 3,280 divided by 1,000. You can see we've got 3.28, and if we want, we can divide it in advance by our molar volume at room temperature and pressure, which is 24. So our answer divided by 24. You can see that our answer. Will come back to just check it if you don't write it anywhere. So N, we said, will be 3.28 divided by 24. Like you already saw on our calculator, the answer is 0.1367. That's the number we'll be using. Like you've already seen, I'm using 4 decimal places usually. Now, we're going to use mole ratios once again. These number of moles we found are for the carbon dioxide. but we're supposed to find the percentage purity of calcium carbonate sample, which is here. You can see there are no numbers in front of these two substances that we want to compare and use for the mole ratio, so our mole ratio is 1:1. And when our mole ratio is 1:1, it simply means there's no change. This amount of moles is the same for the calcium carbonate also. Therefore, to find the mass of the calcium carbonate that was used in these 15 grams, we're just going to say M is equal to N multiplied by MR. Our MR, or our molar mass for calcium carbonate, is 100. You can check it with me. Calcium is 40. Our carbon there is only having one atom, so it will be 12. Then we've got 3 atoms of oxygen. Therefore, the 3 multiplied by the 16, or if you prefer 16 multiplied by 3, you can see our answer is 100. Therefore, we're going to multiply this 100 by the 0.1367. As you can see, we have 13.67. These are the grams of calcium carbonate that are only needed if the calcium carbonate is pure. If you have 13.67 grams of pure calcium carbonate, you'll be able to produce these 3,280 cubic centimeters of carbon dioxide. Since we've calculated that, let's just indicate it. The 0.1367 multiplied by 100, giving us 13.67 grams. Now, our real question that we were asked was the percentage purity. We know that if we use the pure substance of calcium carbonate, we only need 13.67 to produce or yield these 3.28 cubic decimeters. So it means the percentage purity of this calcium carbonate is the ratio pure divided by impure multiplied by 100. As you can see, the pure amount of substance of calcium carbonate that can produce this is 13.67. Therefore, percentage purity will be equal to 13.67 divided by the impure 15 there. The 15 grams of calcium carbonate had impurities. Therefore, the fraction here multiplied by 100% is going to give us the percentage purity. We already have the 13.67, so we're just going to hit division. Our calculator automatically knows we're dividing the answer, and 1/5, and then hit equals. This is the fraction 0.911, and if you know what multiplying by 100, our decimal point will just move twice towards our right. Hence, our answer will be 91.13. Now, I want you to observe this simple thing that I'm going to do here. Make sure you've observed the answer here, or you've written it somewhere. Here we calculated a lot of things. Now I can get an accurate answer if I have the 3.28 divided by the 24. Give me that answer. I multiply this answer by 100 after this step. You can see, and then I have this accurate answer divided by 15. And I have the most accurate answer I can get for this working, 0.9111. As you can see, this answer differs from the previous one we had. It was 0.913333. I hope you wrote it somewhere so that you make this comparison. When I'm doing those calculations, I used the most accurate numbers as possible, and I had 0.911. You saw how I did it. Multiplied it by 100 and got the percentage purity as 91.11%. This is how you can work out the limiting reagents, percentage yield, and percentage purity. You have finally reached the bonus tip section. In today's video, we've got a tip for you that's worth paying attention to. There's a way in which you can avoid wrong percentages, which is whenever you have been given information about all the reactants, make sure to determine the limiting reactant before you find any percentages. Take a look at this example. We've been asked to find how many grams of carbon dioxide can be produced by complete combustion of 14 grams of ethene. If actual yield turns out to be 200 grams of carbon dioxide, what is the percentage yield? In this particular example, you see we haven't been given anything about the oxygen. Therefore, we can simply take it that our ethene is the limiting reactant. We have been given any information about oxygen, so there's no in which we can use the oxygen to find the yield of carbon dioxide. But if you look at this other question, we've been given information about both these two reactants, and using any of them from the information here will be able to give us answers. But one of them is going to give us a wrong answer, and this is the case where you're supposed to be careful and find the limiting reagent, then you calculate whatever is required. Thanks for watching this video till the end. Make sure you watch out for more videos in chemistry about the more concept. Make sure you check the links in the description and make use of the time codes that have been given there too.